This is record to computer. I also record this. All right, so this paper was written by my advisor, Simon Lam, and my formal group mate, Dongyang Li. And I think this one is a very good paper. Although I wasn't an author of this paper, but my dissertation was developed on this paper. Okay, I actually add another layer to this paper. My work is called MDT, which is also a very nice work, even compared to my current work. I would think the dissertation is a nice work. So this slide was made today. I also checked it. I think this slide I made it in 2009 or 2010. I don't remember exactly. Okay, so you can see what kind of slides a PhD student should make. And now that's 15 years later. And we now have more advanced, powerful tools. So you need to make better presentation slides, okay? And you need to do better presentation than me. Okay. So this paper is called Efficient and Accurate Protocol for Distributed delaunay Triangulation on the churn. So I think the key words here, is the distributed delaunay triangulation. Okay. So this paper is somehow related to what we've learned last time, but they are not completely, not closely related. A little bit somehow related. Okay. But I think learning this paper will definitely help you to better, understand what kind of contributions you can make for HNSW, right? And that, I think the authors of HNSW definitely doesn't know this work. Okay, I don't know why, but they didn't do the literature review very well. Okay, let's start. What is a Voronoi diagram? A Voronoi diagram takes an input of a set of nodes, and this set of nodes is in a d-dimensional Euclidean space. So the figure is just 2D, two-dimensional. It actually can be d-dimensional, right? So it's 2D. A Voronoi diagram is a partition of the space, and here is a 2D plane, into cells such that a node U is one of the set of nodes, okay, is the closest node to all points within its Voronoi cell. So do you understand this definition, Voronoi diagram? Anyone don't understand, just speak, okay? Otherwise, I will ask you questions. If you cannot follow, just say it. It's not a shame to say that you cannot follow, because that's kind of like PhD material. It's not a standard textbook material. All right, I assume all of you can understand. Okay, so let's wait. So this is not PowerPoint. I cannot draw something on the picture, which on the screen, which is okay. Fine. How? This is a Google Doc. Oh, Zoom. Annotate. Okay. Okay, good. I want to use red. All right. So this is the Voronoi cell. This is a Voronoi cell of U, okay? So everything, every point is, node is given, but point can be any point, right? So anywhere in this Voronoi cell, they are closest to U compared to other nodes in the Euclidean in the set of nodes. Okay. What happened here? I cannot annotate at the same time of presentation. Okay. Sorry. What? Okay. All right. So this is VCSU. Okay. Wait, what happened again? And this is a delaunay triangulation. The brown links are the delaunay triangulation. So the delaunay triangulation is that if two nodes share a Voronoi edge, that means their Voronoi cells are neighboring with each other. We connect those two nodes. So the delaunay triangulation is a connection of the original set of nodes. Look here, V and U, right? V and U. Their Voronoi cells are neighboring with each other, and they share a Voronoi edge. So we directly connect U and V, okay? And this is called delaunay triangulation. So DT and VD are duals of each other. If you don't understand what is duals, you can Google it, okay, in graph theory. So the definition of delaunay triangulation is like follows. Wait, okay. The reason why I need to use a Google presentation because the PowerPoint slides I made was in PPT, not PPTX, and this computer cannot open PPT. So I have to upload it to Google Sheet and then, no, Google Doc, and then open it in Google Doc, Yeah, so that will bring some trouble. So there is a property of a Voronoi diagram. For example, each point on an edge has equal distance from the two nearest neighbors U and V. Everyone on this edge has equal distance to U and V, right? And that means, okay, yeah. And the vertex at which the three Voronoi cells intersect is the center of the circle passing through those points, U, V, W. Does that make sense? Yeah, okay. Because they have equal distance. So this is the product can be generalized to 2D, to D dimension. So if that's a 3 dimension, what is a circle? That's a ball, right? And what is triangulation in 3 dimension? That's a tetrahedron, okay? Tetrahedron. In Chinese, it's called a 三棱锥, right? Tetrahedron. All right. But those properties also still holds. What is the property of a delaunay triangulation? So the property, there are a lot of properties, okay? One of them is the most fundamental one, is that the circumcircle of any triangle on the graph does not contain another node. That means, look, U, V, and W is a triangle, right? Then you draw a circumcircle of this triangle. It will not contain another node in the set. No other nodes is in this circle. You draw every circumcircle for every triangle, and none of them will contain another node. Okay? And also, see, the Google Doc will have some mismatch on this point. Okay, so it should be a triangulation, all right? Okay. Oh, that's not a triangle. Come on. So yeah, let's see. So greedy, we all learned greedy routing last time, right? Greedy routing for a random graph. Suppose I start with C. I want to find the I start with S. I want to route perform a routing to D. So the greedy routing will always choose the node that is closest to D. So when we start from S, the next hop is U, right? And when we arrive at U, none of U's neighbor are closer to D than U itself. So the routing will stuck at U. It will never arrive at D. And this is called the local minimum. Does that make sense? Do you understand this? All right. So, but with a delaunay triangulation, a delaunay triangulation has no local minimum. It doesn't matter which node you start. It doesn't matter which node you are routing to. As long as you are in a delaunay triangulation, there is no local minimum. And this is proved by a paper written by Bosey and Marine, BM, in 2004. They prove it in 2D, two-dimensional. Okay. And this paper, my advisor's paper, proved that in D-dimensional, I mean, in any dimension, the greedy routing property still holds in a delaunay triangulation. Okay. And they also proved another property, which is also important. Look at the second bullet. If there's no node at the destination location, so you have a location and you perform a greedy routing, right? The greedy routing will find the node which is the closest to the node location among all nodes in the DT. That means if your destination is this D, okay, and there's no node on D, and where your greedy routing will stop, it will stop at V. Okay, if it starts from S, it will stop at V, and V is the closest node to the destination location D. Okay. And what is a distributed delaunay triangulation? A distributed delaunay triangulation means every node only know a subset of nodes, and there is no one. It's a network environment. There's no one knows all nodes. So if you don't know all nodes, how do you calculate the DT? You cannot, right? Because when you have another node, the DT will change. So if you don't know all nodes, how can you calculate DT? They invented a method that it allows everyone only know its nearby nodes, and then the nearby node will be defined later. And eventually, they can calculate a correct DT without knowing all nodes. It sounds like a magic, but they did it, okay? And why this is important? Because this is this is used for in network environment. In network environment, usually when you have when you are a network user, you only know a subset of neighbors. You don't know everyone on the internet, right? You don't know everyone on the internet. And also, this can be helpful for large scale data sets like the vector database. But at that time, they didn't know vector database. But from the current perspective, I think it also benefit to vector database. Why? Because since everyone only know a small set of nodes, that means the calculation on every node is almost constant. Does that make sense? Almost constant. And therefore, the calculation will only increase linearly with the size of the database, right? It only increases linearly. However, if you want to calculate a DT or some other ones for all nodes, would the calculation be linear? I'm not sure. I learned computational geometry, but I don't remember exactly the time complexity of calculating a delaunay triangulation for d-dimensional vector space. But it's definitely bigger than linear. It's probably like log n, but it's definitely bigger than linear, all right? But if you try to distributed delaunay triangulation, that's always linear because you maintain the calculation on everyone in constant. And there are n nodes, right? If everyone is constant, then the total calculation is still linear. Does that make sense? Okay. So I believe even with a centralized computer, the distributed DT calculation is still much efficient than the global DT calculation. But I didn't verify it. I didn't verify it. Okay, so let's go. Say if say a node U and everyone knows a set of nodes called candidate set, CU, okay? So in this example, let's say the candidate set of U includes U, A, B, C, D. And so U only knows these 5 nodes, and U doesn't know E and F and all other nodes. So if U wants to calculate a delaunay triangulation, you can only calculate something like this. It's definitely not a complete delaunay triangulation, right? But from this local delaunay triangulation, this is called the local DT. Local DT, you can find 3 neighbors, A, B, and C. And they prove that if a neighbor on a global DT is included in the candidate set, then this node will also be a neighbor in the local DT. Okay? That means if CU includes all its global DT neighbors in the candidate set, and it really doesn't matter whether it includes more nodes, you can already determine its DT neighbors in the global DT. Does it make sense? Are you all following?
Yeah.
Okay.
Yeah.
So the problem is that how we can include ABC into this candidate set, right? Because we haven't talked about how we can find the candidate set. That means as long as the candidate set includes its DT neighbors, you can determine those are DT neighbors. So as long as every node include their correct DT neighbors in their candidate set, then the localized calculation will eventually result in a globally correct delaunay triangulation. Okay. So the correct neighbors are A, B, and C, right? For U. So NU should be A, B, and C. And CU can be any set. But as long as CU is a superset of NU, then the calculation will be correct. Okay. So the correctness of distributed DT is that if NU, the local DT neighbors, is the same of global DT neighbors for everyone, then we call a distributed DT is correct. Okay, we call the distributed DT is correct. So for example, yeah, why I draw this? I don't understand. But so this is a global DT, right? And previously we have a local DT, but it really doesn't matter whether global DT is equal to the local DT. As long as NU is the same as the neighbors in the global DT, for every node of U, the distributed DT is correct. Okay. So we have theorem 1. Let S be a node for each, be the set of nodes, and for each U, which is one node in S, and U knows its candidate set CU, and obviously CU is a subset of CU is a subset of S. Okay, so no problem with that, right? The distributed DT is correct if and only if for every U equals in S, CU includes all neighbor nodes or DT neighbor nodes of U. That means CU is a superset of the correct NU.
Is this an assumption?
This is a theorem.
Oh.
If that means if CU includes the correct NU, no, CU is a superset of a correct NU, then the distributed is correct. Okay. All right. So this protocol is to build a correct distributed DT for a dynamic set of nodes in a d-dimensional space. Okay. And it also assumes the node will join, leave, failure, which we actually, if we do database, we don't need to care about this because we don't, the database entries will not fail. Okay. It will join, but will not leave and fail. Oh, somehow it will leave. Sometimes it will leave, but it will not fail. Okay. But the internet nodes will fail, of course. So it is proof to be correct for a single join, leave, and a failure. And we can skip it remaining and look at the nodes. Okay. So let's look at how we can construct a DT. There is a algorithm called a flipping algorithm, which we do like this. For example, if U knows all those nodes, okay, so and this is local DT, right? Then how can we determine it's a delaunay triangulation or not? So to construct a delaunay triangulation, we always starting from a random triangulation. So this is a random triangulation. And then for every triangle in this triangulation, we calculate the circumcircle. So now we calculate the circumcircle of VWT and we find a problem, right? Because for delaunay triangulation, the circumcircle of any triangle shouldn't include another node. but this one includes the U node and includes another one. Okay, includes those two nodes. So this definitely is not a correct delaunay triangulation. And the flipping algorithm, once checked with a triangle that violates this condition, the triangle will have a flipping edge like this. Okay, and we keep checking that until there's no triangle or no simplex. So simplex means it's a triangle in high dimensional space. Violate this condition, and we are done. So we have a delaunay triangulation. Yeah, Ryan.
If multiple nodes are violating this rule
We
of
check
you can't,
one by one. We don't care about multiple ones. We only care about one of them. We check one of them, and then the other after.
would it be
Okay.
optimal to check the shortest or like the closest of the potential, or does it check each one individually?
They check everyone individually, I think.
Okay.
Yeah.
Thank you.
So it's getting rid of one of the edge of the. So how does the algorithm know which edge they get?
If you are, I mean, you want to get rid of one of the edge. Okay. Oh, yeah, you are right. So, in that was a algorithm material. So it needs to flip one of the edge. You are asking which edge you are flipping, right?
Yeah.
Probably you need to flip an edge which contains another, simplex like U, another node U, and that node will form another triangle with that edge. Does that make sense? So it includes U in the circumcircle, and the U will give another triangle with the edge V and T. So we need to flip VT with U and W. Okay.
It's like it starts from a triangle, and every time when a node join, it's just randomly connect the new join node with two existing nodes and check if this new triangle follows DT. If not, with this.
Yeah, right. Okay. So now we want to construct a distributed DT in a incremental and iterative process. It's incremental because we assume there are k nodes in the network, and another node joins the network. So we want to prove the protocol will let the k+1 node maintains a correct DT. So we originally have k node and they are correct DT. And now we want to show the protocol will make a k+1 node to be a correct DT. So then by induction, we can make a DT for any number of nodes, right? Does that make sense? It's very similar to induction. Okay. Now we assume there are k nodes and they form a correct DT. And a new node joins the network. So the U will contact an arbitrary node. It could be any node. Let's say W, okay? U knows W, but U doesn't know others, right? So right now, you cannot calculate the correct DT. So U talk to W, and let's assume that U is inside the convex hull of the current node. Do you know convex hull, by the way? Okay. So U is inside the convex hull, and you talk to W. So U says, hey, please run a greedy routing in the current DT and use my location as a destination. So W will run a greedy routing in the current DT. And remember the property of a correct DT, that it will stop at a node V such that V is closest to you among all other nodes, right? Okay, V is fine. And V is closest to you. All right.
Wait.
And yes, Daniel.
What happens if U is not in the context hole?
I almost forget it because that's 15 years ago. I read the paper 15 years and made the slides. But I forgot. But I think there is a way to deal with it because I ran the algorithm and I didn't put the condition that the new node should be within the context hole. Okay.
Okay.
And V, so now U knows V, right? Because W helps to find V, which is the closest node. And actually, another property of DT is that if U and V are, if V is the closest node in U, then V must be use DT neighbor. Okay, so then you will send a message called neighbor set request a message to V. Okay. A neighbor set request a message. And by sending this message, V got this message, right? And now V has its local DT. V's local DT originally includes V and Y and X and W. They are V's DT neighbors, right? And now it includes U. So now it includes 5 nodes. It doesn't include Z because we don't care about Z. Z is a remote node. So V will calculate its local DT again. Now we have U, so the local DT will look like this, the red ones, right? And which doesn't include Z because that doesn't matter. It's a remote one. Okay, so V knows its local DT will change because U joins the network. And V will revise its neighbor set to be Y, U, and W. All right. And V also will tell you by sending a neighbor set reply saying that, all right, you, here is your DT neighbors from my perspective. From V's perspective, use DT neighbors should be Y, W, and X, and of course, U, V itself, right? So V will send you this information, and U will include all these information in its neighbor set. And U will, now the candidate set of U includes U itself and V and X, Y, W. They are told by V. All right. So V will calculate a local DT using this candidate set. And now you find more neighbors in the local DT, which is V, of course, and Y, X, and W. So U knows Y, X, W are the new neighbors in its local DT. So you will send this query, which he previously sent to V, will send it to W, Y, and X and ask them about their DT neighbors. Okay. So you will and here is the optimization. You could send every message, send a request message to every new DT neighbors, but they did an optimization. That is for a each simplex, you only need to check once. So V, it has checked previously. And this Y, X, and W, it hasn't checked. And U, W, X, it hasn't checked. So it only needs to check one node on every simplex. So now it can only need to send to X, and all simplexes are checked. So it just sent to X. So you can send a neighbor set request message to X. All right. And for other not selected new neighbors, they set a neighbor notification. What is a neighbor notification? Which means, hey, you have a new neighbor, which is me. Okay. When X receives a neighbor set request from you, X did similar things like V did just now. So X will include U into its neighbor set, and X will calculate its local DT, which is look like that the red one. By the way, X doesn't know V and W, okay? So X will reply to U, says, now you have two new neighbors from my perspective, which is Y and a Z. Daniel.
Wait, so is this local DT just computed by like the flipping algorithm you mentioned earlier?
Yeah. Local DT is computed
Okay.
by the flipping algorithm.
Okay.
So after you receive this neighbor set, you finally learns its final DT neighbor Z. Okay. And you now realize that all simplexes in its local DT has been checked. Oh, probably not. Probably like U, W, Z are not checked, right? So you will send another neighbor set request to Z. And Z will tell you if it has new neighbors or not. And most likely no new neighbors after this check. So if no new neighbors, the join finishes. And when the join finishes, everyone maintains a correct distributed DT. Okay. So the assumption is that every new node is always placed inside an existing triangle because we assume that it's in the convex hull. One way to achieve this is to construct a bounding convex hull at the beginning. So you set up a number of virtual nodes on the boundary. Then every new node will be inside the convex hull. Does that make sense? Okay. If the assumption does not hold, the new node should send a neighbor set request to every newly learned neighbors rather than just check one per simplex. Okay. So it will be more if you don't have this assumption, then the protocol will be more expensive. All right, takes more time. So they proved this theorem. It says let n denote a new join node, S and S be a set of existing node. Suppose that the existing distributivity is correct, and no other node joins, leaves, or fails at this time. Then, when the join protocol finishes, the updated k plus 1 distributivity is also correct. So that is, they can prove if k is correct, k plus 1 is also correct. By induction, they can prove that if we run the join serially, then it will eventually be a correct distributed DT. Okay. So leave protocol. Leave protocol means there is a node U. I want to leave the network. So you will send every neighbor about its neighbor set. Say you will tell V, okay, my neighbor is XYZWV, okay? So V will use this to calculate its new neighbors. And everyone will use this information to calculate its new neighbors. And the calculation after use leaving will be like this red lines. Okay. So I will skip the details of the correct. And they also proved if S is a correct distributed DT and one leaves the network and tell others, then this K-1 network is also correct. Okay, there's another condition, which is what if you fails from the network by, for example, power outage? Okay, so you cannot tell others about use DT neighbors. In this way, you will prepare a contingency plan for its failure, which includes its neighbors. And you will designate one of its neighbors as a monitor node and put the contingency plan on the monitor node. So if you fails, the monitor node will send the contingency plan to the others. Okay, so this is a failure protocol. By the way, this failure protocol is useless in database, so I skipped the details. Okay. And there is also a maintenance protocol. What does that mean? That means if we have leave, join, failure at the same time, right? What do? A maintenance protocol will keep running periodically. For example, every minute or every 10 seconds. Okay, whatever you call it, it's a periodically. A maintenance protocol will keep sending neighbor set request to the local DT neighbors and receive potential neighbors from local DT neighbors and update the local candidate sets. They will keep doing that just like join protocol. Like everyone will run the join protocol periodically. And in the end, the maintenance protocol can converge. All right. So the correctness of a maintenance protocol is not proved because it can never be proved. Think about it. If you have one node and if you have 100 node and they fail simultaneously, okay, there's no correct DT, all right? Or there's 100 node, you fail 100 node and joins 100 another node, okay? Then how can you prove the correctness? You cannot, right? So they do the experiments and they defined the accuracy as the accuracy of distributed DT is like the number of corrected DT edges minus the number of wrong DT edges over 2 times of the whole DT edges. Why we need the double, the 2 times? Because a DT edge is from one node's perspective. Maybe from the other node's perspective, the DT neighbor look like a different one. So every DT link actually has 2 right, will count twice if we consider the local DT. So if there's no wrong DT edge, then the accuracy is 100%. All right. So initially they put the nodes in a ring, and of course ring is not a DT, right? So they allows the maintenance protocol to construct, and they find that for 2D and 3D, they will converge to, the accuracy will converge to 1 after 4 rounds of maintenance protocol.
Oh, the round means the message exchanging time.
I think that's like how many times you run the, I don't know. Maybe how many times you run the maintenance protocol. Each running of maintenance protocol is like you picking a few nodes to send neighbor set request and get the neighbor set reply. Okay. So they start from a barely connected graph in which each node only knows one other node. Oh, it's not on-directional ring, it's a unidirectional ring. So that's even more challenge. Unidirectional means it's directed graph, and everyone only knows one other. Okay, so they will converge. So this is a join protocol. A number of messages. Look, if the number of messages is 2, how many nodes are joining? I don't remember. Okay, so increase the size from 200 to 300. So new 100 serial joins. You see, the ACE protocol is the bottom one. Okay, the ACE protocol is the bottom one. So we find for 2 dimension, it's very efficient, but it costs a significantly increase for 4D and 5D. So we probably should avoid using very high dimensional space. Okay. The cost of failure. That's not important, so let's skip it. And here we have churn. What is churn? Churn means we have leave, join, and failure at the same time. So when we have churn during, I think, like the 10 seconds to around 100 seconds, there are churn. And after that, the churn stops. And it doesn't run the maintenance protocol. It only runs the join and failure protocol. So it will converge to 98%, 99%. But it cannot converge to 100%. But with maintenance protocol, the ACE protocol, ACE is the proposed one, will quickly converge to the 100% accuracy. 100% means no local minima for routing, right? Okay. So actually, they published another paper in ICDCS 2007, which is an old protocol. It's just called old protocol. I don't know why the name is so weird, but this is called the old protocol. So the ACE protocol is much more efficient than the old protocol. I think the old protocol basically check every neighbor rather than just check one neighbor per simplex. So in summary, we define a distributed DT and its correctness and identify a necessary sufficient condition. And the ACE protocol is to be proved to be correct for a single join, leave, and failure. And I think the most important we need to take away is that first, for a DT, greedy routing always gets you the closest node to the location. You need to remember this, okay? This is very useful for this HNSW. And second, you can calculate a correct delaunay triangulation by running the iterative query. So I would say if we change the HNSW protocol to iterative query, probably we can have better performance in on HNSW. I don't know. Okay, and that's it. Any other questions? I made this slides like 15 years ago.
So age maintenance is not rigorous, very rigorous.
It always help you to converge in experiments, but you cannot prove the correctness. There's no way to prove the correctness.
How do they like first design this driven by intuitions?
Yeah, intuition, you just keep running the join. Everyone will treat itself as a new node, like every, for example, 1 minute. You run join again, run join again, run join again, and yeah, they will converge. Okay, any other questions? Come on, did you read the paper? All right, so let me ask a question. All right. Why HNSW cannot use delaunay triangulation? They use a, near delaunay triangulation graph, which I don't know whether it's near or not. I mean, I think E knows about this. I'm asking other students. E and Xiaoxun would know that. I asked other like Alan and Ryan and Summit and Daniel and Shenzhe. Do you know why the HNSW cannot use a complete delaunay triangulation?
Like it's like didn't the paper say like if it's like high dimensional there can be like way too many edges?
Exactly. Okay, Daniel is a middle school student and he answered he provided the correct answer. All right. So the other student, you need to read papers as carefully as Daniel. Okay, Daniel, you're right. So HNSW cannot use the exact DT because the for high dimension, like for regular data set, it could be like more than 100 dimensions. For 100 dimensions, it's impossible to maintain a DT because that means the DT will include several hundreds of thousands neighbors for every node. And that's too much, too many. And also from the figure, we see that even with like just 5 dimensions, the cost increases significantly. So this ACE probably only work for 2 or 3 and 4. All right. And but you know that in reality, probably for each application, 4 dimension would be sufficient. I don't know. Okay, I'm also thinking about another question. So HNSW, right? If we don't know, let's forget about delaunay triangulation. Let's think about the nearest neighbor. They cannot even guarantee that the nearest neighbor is the neighbor, right? The nearest node is a neighbor. Can they prove that? They cannot, right? What if we wait? They cannot prove nearest neighbor because the node is the graph is not a complete DT graph. And it could have local minima. All right. Can we somehow improve the HNSW to include at least the nearest neighbor, if not all DT neighbors, but just the nearest neighbor? Can we do this iterative query to keep finding the nearest neighbor? I don't know. Maybe we can use run iteration for every node for like 100 times, then probably we can find the most nearest neighbor. I haven't tried, but you can try, okay? Is there a way to design an algorithm that at least you can find the nearest neighbor? Or at least you can find the nearest neighbor for the majority of nodes, if not all nodes. Okay?
Wait, wasn't that the focus of the I think it was the heuristic where it brought in the search to make sure that you don't get stuck on local minimums?
Yeah,
Like
yeah,
with a
right.
well-designed
The
heuristic.
heuristic, but I think the heuristic was designed very roughly, right? I still don't quite understand the details of the heuristic, but if you understand, did they use like the iterative queries? I think so, right?
I believe, but I remember we also discussed in the last like research paper discussion that the at least the pseudocode implementation on the paper itself seemed a bit rough, and that there might be more efficient ways of implementing a
Sure.
heuristic.
Right. So I don't know. If you want to try, you can try. Okay, so this is a research topic. Because if I know, then this is not a research topic. This is a textbook. It's a teaching material. If I know, if I don't know, this is a research. Okay, I don't know, so that's a research topic. You can investigate this. Oh, okay. So my suspicion is that if we use a protocol that's similar to ACE, we probably can somehow, or we use the idea of the iterative request and a reply in ACE, we probably can find some better nearest neighbors than HNSW. Okay, I don't know. All right, I think so much for today. Next week I will be gone, but I wonder if Xiaoxue can lead the discussion. You wanna? We can read the survey I posted in the Slack channel, but some of them are not in the Slack channel. So you please send to the email thread. Send a survey in the email thread. Xiaoxue, can you do that? Independence Day. Do you want to have the discussion on Independence Day? Okay, probably no. Then we have another meeting on the 11th, which I'm not here either. So Xiaoxue can lead the discussion, and we will read the survey paper. Xiaoxue, please send a survey paper to the email thread. Okay. Okay, let's stop.
Wait, to get access to the paper, do we have to be in the Slack channel or are you gonna email it?
Yeah, Xiaoxue will email it.
Okay, thank you.
Or
Thank
I
you.
think I included that in the email thread already. That's a VLDB, right? Written by Purdue University. So okay, you can Xiaoxue can highlight it again. No, I mean email. Yeah. Okay. Bye.